essentially is what we did in chapter 5 with solving trig equations, but we're going to be solving more challenging ones. And the goal is to use identities to make the equations simpler so that we can solve them. And just a reminder, the way that we solved them in chapter 5 was we used cast as one piece, right? We had the trig ratio equal to a certain value, and we could figure out using cast what quadrants that was in. And then the other piece was that if it was a second degree equation, we had to factor it as if it was like a quadratic, okay? So that we're going to be doing a lot more of that today. Non-permissible values with trig equations. So anytime there is I don't think it's going to let me draw thin today. Let's see. No, my little pen thing isn't showing. Okay, anytime there's a trig ratio in a denominator, okay, we have to state non-permissibles. And depending on whether you're asked to solve the question over a particular domain or give the general solution, your non-permissibles sort of have to align with that. Okay, so specific values, I suppose, over a finite domain. Right? So if you're asked to solve like from 0 to 360, you're just going to give a couple of values. Maybe 1, maybe 2. Or general non-permissible values if the domain is not restricted. Okay, and we'll see that as we go today. Okay, now the idea behind sort of using these identities to help us solve equations, the overall idea is that we want to use identities to simplify the equation. So that might mean reducing the number of trig ratios, right? So for example, if we see a cos squared theta in there and everything else is in sine, we can replace cos squared theta with 1 minus sine squared theta. Now the entire equation is only using the sine ratio. That sort of idea. Okay, so we can reduce the number of ratios. That's one thing that we can do. We can also sort of eliminate all of the double angles by using the double angle identities. Okay. And then after that, we're going to treat them the same way we did in our last unit, where you essentially have to factor, usually you have to factor the equation and then solve each piece separately, right? So that part is not different. This extra step is to use an identity to turn it into an equation that's sort of factorable, okay? So for example, let's say we are asked to solve these equations over this domain. Okay. Now, first, when I look at this first equation, everything is in sine and cosine. Those are the only two trig ratios that don't really have anything in the denominator. So in this first equation, I don't need to worry about non-permissible values. Every value is permissible. Okay, so that's one thing that you should always check for. Now, when I look at this equation, I've got a cosine and a sine in there. So what could I do? Yeah? Yes, we can. I didn't even think of that. How many other people thought? That's so interesting. Okay, yeah, so there's two options here. You can take this. Right? Or you could just take the sine squared x and replace it with 1 minus cosine squared x. And at the end of the day, once you simplify, you're going to get the same value because the 1 minus 1 will make 0. Yeah, okay. I like that. Right? So we're going to take this and sub it in here. Okay? But just so you know, you can also just sub for a sine squared x or a cosine squared x. Sine squared x is 1 minus cosine squared x. Okay? So this is going to become 2 cos x plus cos squared x equals 3. Okay? And now what? Yep.
You can subtract 3, and then I think you can...
Yeah, exactly. So now we're going to equate to 0 as if it's a quadratic equation. So we'll subtract 3 from both sides. And I'm just going to rearrange the terms so that the cos squared x comes first, and then minus 3 equals 0. Okay? And this is now factorable. So we're looking for two things that multiply to negative 3 and add to 2. That would be plus 3 and minus 1. Okay? So from the first factor, we would have that cosine x equals negative 3. Okay? So there's no solution here. Because cosine is between negative 1 and 1. So this gives us no solution. But here we're going to get that cosine x equals 1. So if our domain is 0 to 2 pi, where in that domain is the cosine of x equal to 1? 0 and 2 pi. Yeah. Exactly. Okay? All right. So far, so good. Second question. So where could we use a trig identity here? Yeah, so when you see a double angle, if you can take steps to get it out of that double angle, because it's not like you can factor out a sine x, because this isn't sine x, it's sine 2x. Yes? Oh, yeah. Okay. I'll leave them here. If anyone wants to grab one, you can. Okay, so I'm going to replace this with 2 sine x cos x plus sine x. Wow. All right, I'm just going to pause for a minute while you do that. Oh, you know what? I promised you guys I would print more of them for you, and I forgot. I'll do that for tomorrow. I'm going to write it down. I have a to-do list. Okay. It will be done. Okay, so now I can factor out a sine x. Okay, because I have a common factor of sine x, so I will have sine x times 2 cos x plus 1 equals 0. Okay, and from the first factor, I will get that sine x equals 0. And sine x equals 0 between 0 and 2 pi. When x equals 0, pi, or 2 pi. And then the second piece, 2 cos x plus 1 equals 0, so that means that cos x equals negative 1/2. Okay, so here, if cos x is negative, we have to think in terms of cast. And what quadrants would that be in? 2 and 3, yeah. And the reference angle, if cos x is 1/2, that angle would be pi by 3 for the reference angle. So that means this over here is pi over 3, and this is also pi over 3. And so from starting at the positive x-axis, this is 2 pi by 3 or 4 pi by 3. Okay, so there are 5 solutions actually to this equation. 3 here and 2 here over that domain. Okay. All right. What about this guy? Yep.
Could you factor by square?
Okay. I'm just trying to think that through. You could, but it wouldn't be as simple. Like, it would have to be cos x plus root 3 sine x times cos x minus root 3 sine x, but then you'd have a cos x and a sine x still in there. Yeah. Yeah, so I would either replace this with 1 minus sine squared x or replace this with 1 minus cos squared x, but then you have to multiply it by 3, right? So I'm going to take this and replace that with 1 minus sine squared x, and then minus 3 sine squared x equals 0. Okay, and then when I simplify this, I have a total of 1 minus 4 sine squared x equals 0. And this is a difference of squares. Yeah. And it's only 1 trig ratio, which is nice. Okay. So we will get from here that sine x equals 1/2. And here sine x equals negative 1/2. Okay, so essentially, we have to think about what is the reference angle when sine x equals 1/2. And then because we have both positive and negative, the solution will be in all 4 quadrants. Okay, so what angle has a reference angle, or sorry, what's the reference angle here?
Pi by 6.
Yeah, pi over 6, right? So we're going to get this guy, this guy, this guy, and this guy, or these are all pi over 6. Okay, but then of course we have to start from the positive x-axis. So, oh, sorry, not that I wanted to do. I was going to do theta, but we're working in x here. So one of them's pi by 6. This guy over here will be 5 pi by 6 because it's pi minus the 6th pi is 5/6 pi. The next one will be 7 pi by 6. And then the last one is 11 pi by 6. Okay, so all 4 of those angles have a reference angle of pi over 6. And the first 2, like these guys are in quadrants 1 and 2 where sine is positive. These 2 are in quadrants 3 and 4 where sine is negative. Okay? And then this guy, I think I'm going to recopy. I feel like I'm going to run out of room here. So I'm just going to rewrite it down below. We've got sine squared x equals, was it tan x times cosine x? Okay. All right. So what would you do here? Yep. Yeah. Convert to sine and cosine. So we'll have sine squared x equals sine x over cosine x times cosine x. They cancel, but before we cancel, what should we think about? Yes, we have a trig ratio in the denominator here, so we have to think about non-permissible values. And so we need to figure out when is cosine x? Cosine x cannot equal to 0. Okay? Now I think, when I'm trying to think back to my discussion with Mr. Ma, I think you have to put this line in, not just the non-permissibles. Right? So they want to see the whole denominator set not equal to 0. And then you can say, okay, well, where would that happen? Within our domain of 0 to 2 pi, that would happen when x equals pi over 2 or 3 pi over 2. Okay? So both pieces, cosine x not equal to 0, and then x not equal to pi over 2 or 3 pi over 2. Okay. I would imagine that if you just put in the non-permissibles, it wouldn't be that big a deal. But it's just an extra line to write. Okay. All right, so now we can cancel. And when we equate one side to 0, if I subtract sine x from both sides, I end up with that. And so now I can factor because there's a common factor. Oh, sorry. There we go. Just sine x. My bad. Now I can factor. There's a common factor of sine x. So I can take that out. And I'm left with sine x minus 1. Okay. And from here, sine x equals 0. And that happens on the x-axis. So x equals 0, pi, and 2 pi. Okay. And here, sine x equals 1. Where does that happen? Pi over 2. Okay. Yes.
The pi over 2 is no solution.
Exactly. Yes. This is extraneous. Because if you go back to the non-permissibles, one of the non-permissible values is pi over 2. So we have to throw this out. This is extraneous. Yes?
So do NPVs apply to everything regardless of like which trig? Because like we did NPVs for cosec's, for example, but because it's extraneous for cosec's, we're applying to sine x, so like we'll apply it to everything.
So, okay, the key piece here is that you start from the beginning without simplification, because if you were to take this value of pi by 2 and plug it back into the original, on the left side, you would have 1, because it'd be 1 squared. On the right side, you would have 1 over 0 times 0. And 1 over 0 times 0 is, for this course, we'll call it undefined. It's actually called an indeterminate. 0 over 0 is confusing because we don't know what to do with it. If you pay attention to the numerator, 0 over anything is 0. If you pay attention to the denominator, anything over 0 is undefined. So we don't know when you have a 0 over 0. In general, it's an undefined value, but that's because we don't know what to pay attention to first, right? There's a discrepancy there. So the reason why, although it's an answer for sine, it's extraneous, is that if you go and plug that back into the original equation, the left side will not equal the right side. Right? Because on the right side, or on the left side rather, you get 1. On the right side, you get 1 over 0 times 0, which we don't know what to do with. Yeah. Yeah. Okay? All right. So far, so good? Okay. So this next one, okay, solve sine squared x equals 1/2 tan x cosine x over the domain 0 degrees is less than or equal to x, which is less than or equal to 360 degrees. And then we're going to verify our solution graphically. So the graphic piece is just for verification. We need to solve this algebraically first. Okay? So to start out, it's actually going to be very similar to what we just did because we can write tan in terms of sine and cosine. So I'm going to leave the left side alone. Okay. And in fact, we have the exact same non-permissibles in this equation as we did in the last one because the cosine x is in the denominator. Okay? So except the one difference is that in this case, we're not in radians, we're in degrees. So we're going to state our non-permissibles in terms of degrees. Okay, so over here, I'll just say, okay, cos x cannot equal 0. So x cannot equal 90 degrees or 270 degrees. Okay, and now I can cancel that. And I think maybe at the same time, just so that we don't have that 1/2 in there, I'll just multiply both sides by 2. And then on the left side, if I multiply this by 2, and I multiply this by 2, this will be 2 sine squared x equals sine x. The 2 over 2 cancels. Okay? And then I can subtract the sine x from both sides, equate to 0. And then factor. So we will have sine x times 2 sine x minus 1 equals 0. And then from the first piece, I get that sine x equals 0. And we already know actually the solution to that in radians. It was 0 pi, 2 pi. So in degrees, it's going to be 0 degrees, 180 degrees, 360 degrees. And then the other piece is from the second factor, sine x would equal 1/2. And we've already sort of solved that in radians as well. The reference angle was pi over 6, or 30 degrees, right? So this is 30, but it'll be in this quadrant as well because it's in quadrants 1 and 2. So here we'll get x equals 30 degrees and 150 degrees. Okay, now if I want to verify this graphically, then essentially I want to graph the left side and the right side as I see it in the equation, right? So I'm going to enter it in exactly as I see it, not the simplified version, not where I cancel out the cosine x. The only time you can't sort of enter it exactly is when you have the reciprocal ratios, and then like if it's a cosecant x, you have to put in 1 over sine x. Okay, the first thing that I'm going to do actually though is before I graph it, the domain is in degrees. So I'm going to switch my mode to degrees. Oh, it's in degrees. Oh, great. Okay. And now I'm going to graph the left side as sine x squared. So there's no way on the graphing calculator to like put a little 2 in there. So you have to just take the whole ratio and square it. Okay? And then the next one was 1/2, so I'll just put 0.5 tan x times cosine x. Okay. And the other thing that I'm going to do is go to my window settings. And what I like to do for these types of equations is set the window to my domain, because then I'm going to see exactly the solutions that are available and nothing more and nothing less. So I'm going to make my x min 0 and my x max 360. And then I think I like to, with my trig functions, divide it into quarters. So I'll make the scale 90 degrees. Okay. And then we know that, you know, sine and cosine, for example, go from -1 to 1. And tan has that asymptote. So maybe I'll make my y min, okay, -3 and 3 kind of thing. And we'll see where we get. Let's start with that. And then I'm going to hit graph. So there's the sine squared x. And there is the other side, the 1/2 tan x times cosine x. So I want to just, I know I'm sort of running out of space, but I'm just going to kind of copy this down so that you guys can see. Let's make this a little smaller. And then I'll put this over here so I can look at it. Okay, so the blue graph This is for the question we're working on, the graphic solution. I just ran out of space. Okay, we have this. Okay, so it almost looks like the blue one. There's almost like 2 periods sort of thing. So it kind of goes like that. Oh, that's bad. Well, it'll have to do. And then the red one, I really like to change my color. Let's see if the smartboard will let me. No. Okay, shh. Goes like this, where there's an intersection here, and then here, and then here and here, and then here and here. Okay, but can you guys see on the graphing calculator that there's almost like a little break in the graph right here and right here? That's because of the non-permissible. So there's another hole right here. So if you actually go into your graphing calculator, and I'm just going to actually, for the purpose of this exercise, just only graph the second one. And if you go second calc value, okay, and I put in 90 degrees, it will not give me a y value because that's a non-permissible value. And the same with 270. And you can kind of see on the graphing calculator a teeny tiny little break in the graph. And those are for the non-permissibles. But there are 5 solutions here. So if we count the solutions, whoops, now I'm making it bigger. There's 1 here. So that's 0. This would be 30. This is the 150. This is the 180. And then here we have the 360. So 1, 2, 3, 4, 5. Okay. One thing that I do want to emphasize, because I'm not sure if I put any examples in here that do this. No, because it's the general solution. You have to look very, very carefully in these domains to see if the end values are inclusive or not. Because it's not uncommon for it to be inclusive on one end but exclusive on the other. So you might see like a less than or equal to on one side and just a less than on the other. And then if it was like, if this was just a less than, we'd have to take out that solution of 360 degrees. Okay? Okay, questions so far? All right, so we are going to now do basically the same thing, but these are now general solutions rather than solutions over a specific domain. And so all that means is that for our solutions and for our non-permissible values, we have to give the principal angle and then plus or minus the period times n, right? Where n is an element of the whole numbers. So that's sort of the extra piece when you're looking at the general solutions. Okay, but, okay, so here we have a double angle. So with the cosine, with the identity for the double angle of a cosine, you have a couple of different versions that you can use, all sort of based on the Pythagorean identity. Which one would you choose? Yeah. Yeah. Exactly. So knowing that you have a cosine over here, I would pick the version that only has cosine in it, because then you're only working with one trig ratio, right? So that's 2 cos squared theta, or x, I suppose, minus 1. Right? So you do kind of want to be selective in terms of which version you're going to use, and kind of think ahead one step. Right? Now, if you choose the wrong one, you can always do your own substitution with the Pythagorean identity, and then you're back to this anyway. Okay? But now if I subtract cosine x from both sides, then I have a sort of like a second degree trig equation. One thing, sorry, that I just sort of glossed over, but that I should have sort of thought through was the fact that there are not any non-permissible values here because we're only dealing with cosine, right? So I didn't really, I guess I sort of just saw it and was like, oh yeah, there's no non-permissibles, but you should always sort of ask that question so you don't forget about them, okay? All right, so this is factorable. So let's see, we need two numbers that, well, it's gonna be 2 cos x and cos x to make the 2 cos x squared, and then 1 and 1, and we need minus plus, okay. There we go. So I know that many of you have different strategies for factoring these types of things. What I just sort of demonstrated there was guess and check, or trial and error. And honestly, the more you factor, you'll find that this is the quickest if you start doing it. And essentially, the way to factor with trial and error is you know that the first 2 terms are going to multiply to this, and the last 2 terms are going to multiply to this. And in this case, I only had one option for the first 2 terms and one option for the second 2 terms. It was just figuring out which one had the plus and which one had the minus, right? If you want to use something else, like probably you would use decomposition or something like that, that's fine. Okay. All right, so it's factored. So from here, we have that cos x equals -1/2, and here we have cos x equals 1. Okay, and in terms of the general solution, we have to think, okay, so where is cosine negative? In which quadrants is cosine negative? 2 and 3, right? So it's going to be here and here. And then which angle has a reference angle for cosine of 1/2? Pi over 3, yeah. So we have this and this, right? Now, of course, that's just the reference angle, so we have to start at the initial arm, and one of these will be 2 pi over 3, and then for the general solution, we have to say plus or minus 2 pi n, where n is an element of the whole numbers, because the period is 2 pi for cosine. And then the second one would be 4 pi over 3. Pi plus pi over 3 is 4 pi over 3, plus or minus 2 pi n, where n is an element of the whole numbers. So that's from that first factor. And then from the second factor, where is cosine equal to 1? Yeah, 0, right? So also 0 plus or minus 2 pi n, where n is an element of the whole numbers. Okay, so that's the major difference when you are using, looking at the general solution as opposed to the just over a restricted domain. Okay, now where this can get a little bit tricky is I could actually write this as one single solution if I wanted to. Because if you look at, like, think about a peace sign. Our solution is basically here, here, and here, right? So think about that. There's an even spacing between it. If you rotate 1/3 turn, you're going to end up overlapping with this, right? So you could actually write this. The difference when you rotate to get into the exact same position is 2 pi over 3. So you could actually write this as x equals 0 plus or minus 2 pi over 3n, where n is an element of the whole numbers. Yeah?
Should we, like, are we expected to combine them all?
No. So I would say no. For written response, no. But it's possible that you could see something like this on a multiple choice question. Yeah. And if you see something like that and you're confused, what I would do is take your solutions and see which of the options work for your solutions, right? And you should end up with one of the options. Okay? I would say that this one is like an Olympic level question. Where it's more likely to happen is if you do a half rotation or a quarter rotation, right? So, but I'm just kind of pointing out that it's possible. It's possible. Okay, this guy. All right, so where would you start here? Yeah, change this to 1 over cosine, right? So we're going to get 3 cosine x plus 2 equals 5 over cosine x. Okay, lots of cosines in the denominator today. Yeah, I think we're not even going to get a sign in the denominator. Oh, well, that's okay. Yeah. Yes, but first, before we multiply by cos x on both sides, non-permissibles. So the non-permissibles here have to be general as well, right? So cos x cannot equal 0. So x cannot equal pi over 2 plus or minus 2 pi n. Or x cannot equal 3 pi by 2 plus or minus 2 pi n. N is an element of the whole numbers. Okay? Now, yes. Yes. So this is an example where, yeah, I would sort of expect you to recognize that you can do that as 1, because essentially the non-permissibles are happening on the y-axis, right? So you start at pi by 2, you do half a rotation, you get down to 3 pi by 2, do another half rotation, get back up to pi by 2, right? Yes? I don't think so. But again, you have to recognize, right? So really, you could write it as x cannot equal pi over 2 plus or minus pi n, where n is an element of the whole numbers. Yeah?
Weird question, but if it doesn't specify whether it's in degrees or radians, can you find it?
Good question. Did you guys hear that? Okay, so if it doesn't specify whether your solution is in degrees or radians, could you do either? Well, no, but I think that's a reasonable question. I would say yes, you could choose. Yeah. Right? If we're not specific, that's on us. Okay? All right, so now we're going to multiply both sides by, I'll just put brackets around the whole thing. Okay, so when I distribute that in, I have 3, oh, weird, cos squared x plus 2 cos x equals 5. Okay, and then I can equate to 0 and hope that this is factorable. I think it is. It would be really awful to give you one where you had to use the quadratic formula. That would not be very kind. But I suppose it's possible. But this is factorable because we're looking for 2 numbers that multiply to negative 15 and add to 2. That's factorable. Okay, so just again, I know that some of you don't want to hear this, and that's fine, but just shut your ears for a minute if you don't want to hear it. I just want to show you how easy this is to do by guess and check. And what I look for is how many possibilities could you have as the first 2 terms, and how many possibilities could you have as the last 2 terms, right? Now, if this coefficient is prime, there's only one way to get 3. It's 1 and 3. So you've got to have 3 cos x and 1 cos x. And if this is prime, one of these has to be a 5 and one of them has to be a 1. And then you just have to figure out the negative signs, right? And when you practice this even more, guess and check, you'll know that if this number is not super big compared to these two, more likely the bigger number is with the bigger number, right? And it's just practice. And it actually works out that way, right? And this, then what I do is like, okay, 3, 5, which one has to be positive, which one has to be negative? The 5 has to be positive to make +2. So -3 + 5 gives you the +2, right? So again, I just want, some of you are going to be doing factoring for a lot of factoring for many, many years to come. And so if you try out some of these other strategies, you'll start to recognize patterns. Okay, but again, if you want to use decomposition, or some of you guys have other tricks up your sleeve, fine, I don't care. Okay, so I'm going to have to finish this one down here. Okay, so from the first factor, 3 cos x plus 5 equals 0. That gives me cos x equals -5/3. And that's more than negative, or it's, I suppose the absolute value is more than 1. So there's no solutions here. You're like, yes, no solutions. Okay, and then the other one is that cos x equals 1. And there, that happens starting at 0 every 2 pi. So x equals 0 plus or minus 2 pi n. Yeah.
It can't be -5/3. Why is it?
Because cosine of x has to be a value whose magnitude is less than or equal to 1. And if you think about cosine as being adjacent over hypotenuse, the adjacent cannot be larger than the hypotenuse, right? So that's one way of thinking of it. You can also think about it in terms of the graph. If you look at y equals cosine x, right? The amplitude is 1, so it goes between 1 and -1, right? -5/3 is not within the range of y equals cosine x. Yeah. Okay. Last question. You guys ready? This guy over here. Okay, so I am going to rewrite this one down below because I am writing very big today, obviously. So this one, was it 3 sine squared x? Okay. Oh, I want to talk about this one. There's a bunch of substitutions that we could do here. That's a good question. Okay, what are some ideas? Yep.
Turn this side, I just put me in a weird situation, but I got 1 out of the Pythagorean theorem. But
Love it.
Then I just got 3 is equal to 2.
Okay, you're getting there. We're gonna do this a bunch of different ways. I love that. We're gonna look at that though. Yeah. Yeah. Okay, so one option is to take this, the cos squared x, and replace it with 1 minus sine squared x. Okay? And what we will get is that 2 sine squared x plus 1 equals 2. So 2 sine squared x equals 1 if I subtract 1 from both sides. And then I divide by 2. Okay. And if I take the square root of both sides, sine x will be plus or minus 1/√2. Oh, yeah. Or √2/2. Or that. Okay. All right. So that's one option. What's another option? At the end of the day, we should get the same solution, no matter which substitution we do. So one option is to sub for the cos squared x. What else could we do? Yeah, sub for the sine squared x. Now, when we do that, we will have to multiply whatever we sub in by 3, but we could totally do that, right? So we could go 3 times 1 minus cos squared x, and then plus cos squared x equals 2. Okay, and now what you're going to get is 3 minus 3 plus 1, so plus 2, no, minus 2. Cos squared x equals 2. Okay, and if I subtract 3 from both sides, I will get negative 2 cos squared x equals 2 minus 3 is negative 1. And divide both sides by negative 2. 1/2. And we end up with the same solution, but now it's cos x equals plus or minus root 2 over 2. But remember that the angle that has that trig ratio is pi over 4 or 45 degrees. That's the only angle where sine and cosine are equal to one another, right? Okay. And then when I was looking at this, I was like, oh, there's a third thing that you could do. Yes?
Could you make the equation a difference identity for cosine?
A difference? Okay.
It's like 3 sin x plus cosine.
Okay, you could. That's a good question. Could you turn it into a difference identity? So you mean like putting in a double angle?
Yeah.
Okay, you could, but I wouldn't go in that direction because typically when you start putting in double angles, it makes the equation more complicated than what you started out with. Okay? But the one that I thought of, and we'll solve this at the end of the day, you'll end up getting the same thing that we got here. But one thing that you could do is the original equation, where am I? There I am, was 3 sine squared x plus cos squared x equals 2, right? What if I broke this up into 2 sine squared x plus 1 sine squared x? That would still equal 3 sine squared x. Okay, so I'm basically breaking this up into 2 parts. Then I add a cosine squared x. Okay, now this part equals 1. You could do that too, right? So you will end up with 2 sine squared x plus 1 equals 2. Now I'm going to stop that one there because in the first thing that we did, we got down to that same line. Okay? But yeah, there's a number of ways that you can go with this Pythagorean identity. And at the end of the day, if you reduce the number of trig ratios down to 1, you're in good shape no matter which substitution you do. Okay? So back to here, let's just solve this. So the trig ratio, or the angle rather, the reference angle that has a trig ratio of root 2 over 2 is pi over 4 or 45 degrees, right? So if you think about this in terms of the coordinate plane, cast, right? We have the positive and the negative. So it's going to be in all 4 quadrants. So we're going to have 1 here, 1 here, 1 here, and 1 here. And these are all pi by 4, right? So this would be one where it would be kind of nice if we could write this solution as one solution rather than 4, right? One way of doing it is to say, okay, I'm going to take each of these individual angles and write that as a general solution. So then I would have to go x equals pi over 4 plus or minus 2 pi n, right? All that rest of the stuff. The next one would be 3 pi over 4 plus or minus 2 pi n. N is an element of the whole numbers. The next one is like pi plus a quarter pi is 5 pi by 4. Plus or minus 2 pi n. Ooh, weird. And then the last one is if I do one, let's see. I think I can fit it in here. There we go. But that's like 2 pi minus a quarter is 7 quarters. So 7 pi by 4. Plus or minus 2 pi n. N is an element of the whole numbers. Okay. Now this is one option, but it's a little tedious and redundant, right? Yes.
All the reference angles are separated by 90 degrees.
Yeah, exactly. So look at what this x kind of looks like, right? It looks like the axes, but it's been like turned 45 degrees or pi by 4. But in between each of these solutions is a right angle. So if you start with the first one and do a quarter turn, that's either 90 degrees or pi by 2, you're going to get all the other angles, right? So we can actually write this as a single solution. X equals pi by 4 plus or minus a quarter turn, pi by 2n, where n is an element of the whole numbers, right? And that would be the simplest way of writing the solution to this question. Now, what I find is when I draw it, it's easier for me to see that, right? So I would recommend doing that because you can't always do that, right? So if you think back to the question that we got where I think the trig ratio was plus or minus 1/2, and that reference angle is pi by 6. Now the rotation is different between each angle. The angles between the solutions are different. So you can't get away with that in that situation. And you can kind of see if you draw it fairly accurately using symmetry, whether you can reduce the number of ways you write the solution down to 1, right? Okay. That's it for today. That's it for this unit. Yeah.